in the last lecture, we saw the basic structure for propagating light, and that was optical fiber. We also saw different windows in which the optical communication took place. So, to start with, the optical communication started in 800 nanometer window. Later on, it was shifted to 1300 nanometer window, and today the most of the optical communication takes place in 1550 nanometer window. We also saw the basic characteristics of light. That means, if we consider light as an energy source, then it has parameters like intensity of light, the frequency of light or the wavelength of light, and the spectral width of light. However, if we treat light as an electromagnetic wave, then the vector nature is captured by a parameter what is called the polarization, and we saw that an electromagnetic wave in general has elliptical polarization, which in limiting cases could be linear polarized or circularly polarized. We also saw that if you take a very wide band source, then there is no very definite state of polarization defined, and that polarization we call as a random polarization. So, coming now to the structure, that is the optical fiber. Today we discuss the propagation of light inside the optical fiber. As we mentioned last time, the light can be considered like a ray in the simplest possible model. So, if we consider a source of light, the phase fronts are moving out of the source, and if we draw the lines which are perpendicular to these phase fronts, then we get those fictitious lines what we call as the rays. So, in the simplest possible form, the light can be treated as a ray. Later on, we will take the advanced version of the model, and that will be the wave model, and finally, we have to take the model which is the quantum model, where light would be the combination of photons. So, today we take the simplest possible model, which is the ray model, and we ask that if you were to launch a ray inside the optical fiber, what are the constraints on propagation of light in a bound structure like optical fiber. So, today discussion is mostly going to be around the propagation of light inside the optical fiber in the form of rays. So, as we discussed yesterday, the optical fiber basically is a solid glass rod which consists of a inner structure which is called core and an outer shell which is called cladding. So, for propagation of light, essentially these two layers, the core and the cladding, are the important regions. However, to support this structure mechanically, we have some other layers what are called the buffering layers, but that buffering layer does not have any role to play as far as propagation of light is concerned. So, today we essentially investigate if you have to launch a light inside the core, under what condition the light will propagate inside this core over very long distance without much loss, and then we find out some conditions, the efficiency parameter or the data rates and other things related to the propagation of light inside the structure. So, firstly, let us say that if I had a structure, consider a simple glass rod, and this is the section of that. One thing you would note that if I put a ray of light from this side inside this ray would get inside this medium which is glass. So, is going from air to glass. So, ray will go like that, and then again it will reach to this interface, it will again go away and this will come out. So, if the ray was sent on this optical fiber from the side walls, then the ray will simply cross this structure and will never get guided inside this core. So, one thing is immediately clear that no matter how much light is there surrounding the optical fiber, if the light is impinging from the sides of the optical fiber, there is no possibility of this light getting guided along the core of the optical fiber. That means only possibility if you have to send the light inside the core is that the light has to go from the tip of the optical fiber. So, if the light goes from the tip of the optical fiber, then it will get inside, and if you have a reflection at this boundary, it will get reflected like this, it will get reflected like this. So, through multiple reflections, the light ultimately will get guided inside the core of the optical fiber. So, what we note is that if the light has to be guided inside the core, it can be launched inside the structure only through the tip of the optical fiber. No matter how much light is present surrounding it, the light can never get inside the structure, though it can cross the structure. So, if the tip is not exposed to the light, no light can get inside this core of the optical fiber. And same is true otherwise also, that if the light was propagating inside this optical fiber, no light will come out from the sides of the optical fiber, it can only come from the tip or the end of the optical fiber. That is what precisely we talked about the security inside the optical fiber, that if the tip is protected for the optical fiber, from the sides of the optical fiber no light can get inside the core or no light can come out of the core. So, now we essentially ask a question, if you have to launch a light inside this core, at what angle the light should be launched from the tip of the optical fiber, so that there is a total internal reflection at this interface, which is the core cladding interface. At this point, we may ask, would a partial reflection suffice? Suppose the reflection was not total internal reflection, but suppose the reflection at the core cladding interface was partial reflection. You will see that very quickly there will be leakage of energy, because part of the energy will get transferred to the cladding, which will leak out. So, within a very short distance, the power will be lost. So, total internal reflection is extremely essential if you want to have a sustained propagation of light over very long distance. So, even a smallest possible leakage of light because of partial reflection here would take away most of the power within a very short distance. So, that is the reason we say that the light has to be launched inside the core of the optical fiber, such that the light get total internally reflected at the core cladding boundary, and then through the multiple total internal reflections, the light will be guided along the core of the optical fiber. So, since we are talking about light rays now, first we know that in the ray model, the light obeys what are called the Snell's law. That means, if you have a medium N1, which is here, and the medium N2, which is above this line, and if a ray is launched at an angle phi 1 with respect to the normal, which is called the angle of incidence, then the light will be refracted into the second medium, and suppose the refracted ray makes an angle phi 2 with respect to the normal, then we have the Snell's law, which says N1 sin phi 1 is equal to N2 sin phi 2. Note here, the angle which we are measuring here are measured from the normal to the interface. So, if this medium is rarer compared to this, that means if N2 is less than N1, then phi 2 is greater than phi 1. So, as we increase this angle phi 1, this angle becomes close to 90 degrees, and at what is called the critical angle, this angle will become equal to 90 degrees. And beyond that, if we launch a ray, essentially the ray will be reflected into this medium. That is what the Snell's law says. So, first thing is clear now, that if you want to have a total internal reflection, two conditions have to be satisfied. Firstly, that this medium should have a refractive index higher than the refractive index of this medium. So, in terms of the optical fiber, what that means is that we must have the material chosen for core in cladding such that the refractive index of core is higher than the refractive index of cladding. This is the trivial condition. Then we ask a question, once we have chosen that refractive indices for core and cladding, now if the angle phi 1 is less than critical angle, then this ray will be refracted and there will not be total internal reflection. So, this angle phi 1 has to be greater than certain value, then and then only you will have a total internal reflection at the core cladding boundary and you will have a sustained propagation of light. Before we get into this analysis and ask a question, what is the angular zone from which the light is accepted by the optical fiber? Let us first try to physically see how the light ray can be launched inside an optical fiber. So, one possibility is that if I have the core of the optical fiber, I can launch a ray from the tip of the optical fiber such that it lies in a plane containing the axis of the optical fiber, a thing which is shown here. So, if I take a plane which is passing through the axis of the optical fiber, which is the plane of the paper in this case, and if I launch a ray which lies in this plane, which is called a meridional plane, then you will notice that the ray will be refracted, come here, will get total internally reflected, but this ray will always remain in the same plane. So, through multiple total internal reflections, the light will get guided, but this ray will always remain in this plane. Or in other words, if I now consider the set of rays which are going from the tip of the optical fiber, any ray which is launched in a particular plane always remains in the same plane. And since I have infinite planes which are passing through the axis of the optical fiber, essentially I have an ensemble of rays which go like that. Again they will come and get total internally reflected and come here, and they will again join together and so on. So, if I look at one possibility, this is the axis of the optical fiber, the ray is launched like that, get total internally reflected like that. But when I am talking about one ray, actually there are set of rays which are going, which are making same angle with respect to axis. So, I will have thing will be going like this also, and so on. So, what we notice is that in this case all the rays start together, travel the same distance, again they come and meet at the axis of the optical fiber, again they go like that, again meet at the axis of the optical fiber, and so on. So, in this case essentially you have the rays again and again meeting on the axis of the optical fiber. And as a result, you expect that you will have the maximum intensity at the axis of the optical fiber. So, if I consider the rays which are launched in a plane containing the axis of the optical fiber, then the ensemble of these rays would produce a light intensity distribution inside the optical fiber, which would have a maximum intensity at the axis of the optical fiber. On the contrary, you may say that we can launch a ray deliberately at an angle such that this ray does not lie in the plane containing the axis of the optical fiber. So, let us say suppose I had fiber like this, instead of putting a ray which goes like this in the plane, suppose you put a ray which goes like this. Now, this ray, you can work out that this ray will never now lie in the plane containing the axis of the optical fiber. So, the ray will go like this, it will go like that, it will go like that, it will go like this, and so on. So, if the ray is launched at an angle with respect to the plane containing the axis of the optical fiber, then the ray will never intersect the axis of the optical fiber. In fact, it will go on spiraling around the axis of the optical fiber. So, it comes from here, it will come here, it will come here, it will come here, and so on. These rays are called skew rays. So, in the previous case we have meridional rays which always intersect the axis of the optical fiber, and that is why I give you the highest intensity at the axis of the optical fiber, whereas the skew rays never meet the axis of the optical fiber, and as a result they have low intensity at the center of the fiber. So, now when the light is launched inside the optical fiber, there are two possibilities of intensity distribution, and later on we will see what do they correspond to. But there are two possibilities. In one possibility, you have an intensity distribution which is maximum at the center of the optical fiber, and other situation where at the center the light intensity is minimum. Or in other words, the light essentially is confined to the annular ring of the cross section of the core. So, at the center we have very low intensity and the light essentially is confined to the annular ring. So, light propagates in this form as if the core is not a solid rod, it is like a hollow rod, and most of the energy is just confined to the rim of the core of the optical fiber. So, there are two possibilities. That means, for launching of the light inside the optical fiber, either the light can be launched in the form of meridional rays or the light can be launched in the form of skew rays. For the simple analysis, let us say that the light is launched inside the fiber in the form of meridional ray. So, let us take a cross section of the optical fiber. So, this is the core of the optical fiber with a refractive index N1, and this is the cladding surrounding the core of the optical fiber which has a refractive index N2. And let us say we launch a ray at an angle theta 0 from air, or in general you can see there is a medium which has a refractive index N. This ray now goes inside the core of the optical fiber at an angle theta. The ray reaches to the core cladding interface, and then depending upon what is the value of theta naught, either may get refracted into the core cladding medium or will get totally internally reflected inside the core. So, if the ray was launched at an angle which is beyond certain value, then this ray will get refracted. As I reduce the angle slowly, I will reach to this angle corresponding to this red line, for which the ray at this interface will be launched at the critical angle. So, ray will travel parallel to the core cladding interface, and if the angle is smaller than this, then the ray will get totally internally reflected. What that means is that if I had a light source which could send the rays of light at all possible angles from the tip of the optical fiber, the fiber accepts only those rays which have a launching angle less than the angle corresponding to this red line, this quantity. Let us call this angle as theta 0 max. So, what that means is that for a given light source which is capable of sending light from all directions, the fiber is selective in choosing only light coming from a certain cone, or in other words, there is some kind of a light launching efficiency associated with the optical fiber, because only this cone corresponding to the theta 0 maximum, that is the cone essentially is going to get launched inside the optical fiber, which will be propagating in the core over long distance because of total internal reflections. All these rays which are beyond the red line, they will get refracted, and that's why that power will simply leak out. With this understanding, that one can simply apply the Snell's law at the two boundaries. One can apply Snell's law here, one can apply Snell's law here, and ask what is the value of theta 0 maximum in terms of the core cladding refractive indices. So, if I apply Snell's law at this point, I have here n sine of theta 0, that will be equal to n1 sine of theta. So, we can draw the Snell's law that n sine of theta 0 that will be equal to n1 sine of theta. This angle phi, which is the angle of incidence at the core cladding boundary, which is nothing but 90 minus this angle theta. So, we can write here n1 sine of pi by 2 minus phi, or is equal to n1 cos of phi. Now, at the critical angle when this ray is launched, we have here n1 sine phi. This angle now is pi by 2, the angle of refraction in cladding. So, that will be equal to n2 pi by 2. So, that will be equal to n2. So, from here I can find out the value of the sine phi corresponding to the maximum launching angle, and that will be equal to n2 upon n1. We can substitute, and I can get a value of cos phi. This is what is needed here. So, that gives me square root of 1 minus n2 square upon n1 square. If I substitute now this value of cos phi into this expression, from here I get the maximum launching angle for optical fiber, that will be n1 cos phi divided by n, that will be equal to square root of n1 square minus n2 square upon n square. Invariably, since we launch light inside the optical fiber from air, n is equal to 1. So, for air n equal to 1. So, we have a sine of theta 0 maximum, that is equal to square root of n1 square minus n2 square. Since this quantity is telling you the light collection efficiency, or it has an effect very similar to if the wave was coming or if the energy is coming and you are having some kind of a aperture sitting in front of it, the energy is tapped by that aperture. We call this parameter sine of theta 0 maximum as the numerical aperture of an optical fiber. So, numerical aperture is one of the most fundamental parameter of an optical fiber, and that essentially defines the light launching efficiency of an optical fiber. So, we have this parameter what is called numerical aperture, which is equal to sine of theta 0 maximum, and this, as we saw, is square root of n1 square minus n2 square. So, what we find from here, that if we want to have a very high light launching efficiency, then this quantity should be as large as possible. Since we have already identified the material for transmission of light, that is glass, so I have to make the core of glass. That means the refractive index of glass is more or less fixed, that is equal to 1.5. So, I cannot change the value of this quantity n1. So, only possibility we have is reduce this parameter n2 to as low a value as possible. Now, since this quantity n2 is always greater than or equal to 1, the best situation would be if I make n2 equal to 1, and then I get the full launching efficiency, because that time in that case this angle will be equal to pi by 2. But if I make n2 equal to 1, essentially what we are saying is you remove the cladding. So, as far as the light launching efficiency is concerned, the cladding is an undesirable feature, because if we had a cladding, then n2 will be greater than 1, and then you will have a light launching efficiency which will be reduced. So, in the first look it appears that although the optical fiber structure is consisting of core and cladding, the cladding is an undesirable feature because it reduces the light launching efficiency. However, if you think little deeper, what you will realize is that light launching parameter is one of the aspects of optical fiber. One can ask a question, was our prime goal to put the light inside the optical fiber? If you take a light source and you can put that light very efficiently inside the optical fiber, but if it does not carry any information, even with high efficiency, that propagation is not of any use to communication. So, one can ask a question that instead of continuous source of light, if we put a light in the form which can carry information, then what are the implications of the refractive indices of the coherent cladding? So, numerical aperture, which is the efficiency, this is one of the issues. But another issue is that if you wanted to send the information on optical fiber, then the light cannot be of continuous nature. You have to change the parameter of light. So, let us say we have a light which is pulsed. So, you are sending the light pulses, and now when you put the light inside this core, since any ray which is launched within this cone can be totally internally reflected and will get guided, you can say that now the rays can go at different angles, and that's why they travel different distances. So, if I consider a pulse of light here, the pulse energy will get divided into different rays. One ray will go like this, which was launched straight. The energy which was launched at an angle slightly higher than this will go by this path. The energy which is launched at this angle will essentially go by this, and so on. So, what we see is that the pulse of light which was launched here, from here, the pulse which has gone by this path has travelled a distance which is this. The pulse which has gone by this path has travelled a distance which is this. But since you are having the rays which are distributed continuously in this cone, essentially you have the pulse arriving, some energy arriving at this distance after some time, then after some time here, and so on. So, the pulse which was very narrow at the launching point, when it reaches to this location, the pulse would be having a spread which will look something like that. Or in other words, you have a pulse broadening phenomena because of large number of rays which are going inside this optical fiber, and then these rays are effectively traveling different distance along the axis of the optical fiber, because this is going by this path. So, then one can ask, if I consider two rays, one which is going along the axis and one which is going along the maximum possible angle, theta 0 maximum, what is the time difference between these two? And that's what essentially will give me what is the pulse broadening which you are going to get on the optical fiber. So, the time difference between the two extreme pulses, that essentially would be given by this. You can simply calculate, you can find out if this distance is L, this angle is given. If you apply again the Snell's law and find out the difference in the time, the light is travelling with the same velocity which is c by n1 by this path. So, I can take a projection of this on this and I can find out what is the time difference. I get delta t, that essentially will be given by this. And as we know that within this time, if I transmit another pulse, the pulse will start overlapping with each other and essentially data will be lost. So, for a given distance L, we cannot transmit another pulse within this time. And since the bandwidth or the data rate is of the order of 1 upon delta t, essentially we find that the bandwidth now is related to this quantity n1 minus n2 and also n2, which is the refractive index of the cladding, n1 upon n2. So, ideally if you wanted to send a very high data rate, this broadening of the pulse should be as narrow as possible. Now, since this delta t, what we have here, is related to the refractive indices of this medium. You can look at two quantities here. One is the ratio of N1 upon N2 and another quantity is N1 minus N2. L is the distance along the optical fiber, C is the velocity of light. So, what we find is that the delta T is proportional to the ratio of N1 upon N2 and it is also proportional to the difference of N1 and N2. Since the medium for core is identified as glass, N1 is 1.5, N2 has to be less than N1. So, at most its value can range between 1 and 1.5. So, this ratio N1 upon N2 is very close to 1. It can range only between 1 and 1.5. So, essentially what we are saying is that this quantity delta T is depending on this quantity, which is N1 minus N2. And if you have to make this quantity as small as possible, the difference between the refractive indices of core and cladding has to be as small as possible. So, now we have contradictory requirements. As far as the numerical aperture is concerned or the light launching efficiency is concerned, we want difference between N1 and N2 as large as possible. And as far as the bandwidth is concerned, we want this difference N1 minus N2 as small as possible. So, now the question is whether we should be guided by this parameter or this constraint, or we should be guided by the numerical aperture. The answer essentially lies in the application for which you are using the optical fiber. If we use the optical fiber for sensor kind of application where we want to measure very weak light, then we cannot afford to lose any light. Or in other words, we must have a very high launching efficiency inside the optical fiber. So, in those situations, essentially we use the optical fiber which have a very high numerical aperture, or we can use the fiber which do not have any cladding. Whereas, if we go to communication where bandwidth is a rather important parameter, launching efficiency of course is, but bandwidth is of much higher importance, because unless we have a bandwidth we will not be able to send the information on the optical fiber. So, for communication purposes we have to make the difference between N1 and N2 as small as possible. Or in other words, for communication purposes, the core is an integral part of the optical fiber. If you remove the core, you will have a bandwidth which is extremely small, because this difference will become very large, and then you will not be able to send substantial high speed data on the optical fiber. So, most of the communication fiber, this difference is made as small as the technology permits, and that is the reason typically for communication fiber the difference N1 minus N2 is of the order of about 10 to the power minus 3 to 10 to the power minus 4. So, what that means is that the core and cladding, although they are two different regions, the difference in the refractive indices of these two regions is extremely small. So, essentially we have the same glass which forms the core and cladding, only inner portion of this glass rod is doped with some material. So, the refractive index increases little bit, or on the outer shell you reduce the refractive index by a very small amount, and that rod essentially becomes an optical fiber. So, this gives us very important now conclusion that for communication purpose, whatever fiber we use, the difference between the refractive indices of core and cladding has to be extremely small, and then only you will be able to transmit a high bandwidth signal on the optical fiber. You may do some calculation to find out that if N2 was equal to 1, this quantity N1 will be 1.5, N1 minus N2 will be 0.5, and if you calculate this bandwidth will turn out to be as low as something like few hundred kilohertz or few hundred kilobits per second. this bandwidth is much smaller than what even a twisted pair can afford. So, what that means is that unless we have a cladding in the optical fiber, this structure will be a worthless structure, because it will be able to support a bandwidth which will be even worse than what the normal twisted pair or coaxial cable can support. So, any useful optical fiber for communication has to have a cladding, and that cladding refractive index should be as close to the refractive index of core as possible. With this now, let us now look at the total internal reflection phenomena in a little more detail. Firstly, what we find here is that if we consider the light launch inside the structure, any ray which is within the cone of this theta 0 maximum will get guided because of total internal reflection inside the optical fiber. So, as far as the ray model is concerned, it appears that is a solid cone of rays enters the optical fiber, and essentially through multiple reflection this cone propagates. Let us now try to put the phase fronts behind the rays. But as we mentioned earlier, the rays are only the fictitious lines which we have drawn. Essentially, they are the phase fronts which are moving. So, if you put the phase fronts behind these rays, then ask a question that is this understanding correct, that any ray which goes within the solid angle of this theta 0 maximum would get guided inside the optical fiber. So, let us look at the total internal reflection phenomena by putting the phase fronts behind these rays. So, firstly, let us say we have this core cladding boundary. There is a ray of light which goes, get total internally reflected, and let us at the moment consider only one interface. There will be another one here through multiple reflection the ray is going, and these are the phase fronts which are supporting this ray. So, when the ray is reflected, these are the phase fronts corresponding to this ray, and so on. So, let us say we have these green lines and red lines which tell you the phases of the phase fronts. Let us say the green shows you 0 and this is red shows you pi. So, you have a 0 pi, then 2 pi and 3 pi and so on. Similarly, I have here 0 pi, 2 pi, 3 pi and so on. So, what we find in this region, that the phase fronts corresponding to these two rays, they overlap, they intersect, and whenever a red and green phase front intersects, you have the two optical fields which are out of phase, because the red line has a phase of odd multiples of pi and green line has phase of even multiples of pi. So, whenever a red line and the green line intersect, the light fields cancel each other. So, we have a 0 intensity. Whenever a green and green light intersect, that time we have what is called a constructive interference, and you have a maximum intensity. Similarly, when a red and red line would intersect, you have a constructive interference. So, you have a maximum intensity. So, whenever a red and green line intersect, I have a 0 intensity because of cancellation, because of destructive interference. And whenever a red and red or green and green lines intersect, that time we have a constructive interference and we have a maximum intensity of light. So, now if I consider a cross sectional line, a line perpendicular to the core cladding interface, and I ask what is the variation of light intensity in this direction. So, we get a light intensity which will typically look like that. Wherever a green and green line is intersecting, I have a maximum intensity. Similarly, red and red is intersecting, I have a maximum intensity. Here, this point will correspond to red and green intersecting, I have a 0 intensity and so on. So, in this medium where total internal reflection has taken place, the light intensity essentially varies from maximum to 0, and so on. So, you have a what is called the standing wave kind of behavior of light intensity pattern in a region where there is total internal reflection, that is inside the core. So, inside the core we have the intensity distribution of light, which would be like maxima, minima and so on. If we go to the wave theory of light, it tells us that at total internal reflection, the light intensity is not 0 in the second medium. In fact, if I go to the ray model, this concept is completely missing, because what the ray model says is that at total internal reflection, light is completely reflected in this medium, and it does not say anything about what is happening in this medium. However, if I take light as an electromagnetic wave, it has electric and magnetic fields, and if in this region if you have electric and magnetic fields which are finite, then suddenly the electric and magnetic fields cannot go to 0 into second medium, because you should have a continuity of the fields. So, the ray model in fact does not tell you the correct picture of total internal reflection, because it simply says the total power is reflected at this boundary at total internal reflection, and it does not say anything what is happening on the other side of this boundary. So, if we use the wave analysis, then we find that at total internal reflection, the fields are present in the second medium, and these fields exponentially decay as we go away from this interface. And larger this angle compared to the critical angle, more sharper will be the decay of these fields from the core cladding interface. Nevertheless, these fields are going to extend to infinite distance, at least theoretically. Or in other words, what we are saying is, no matter how far away I go from the core cladding boundary, I will always have these fields present which are exponentially decaying, and these fields are as important as the field which are these fields, because you have to maintain the boundary conditions at the core cladding interface. So, that means we must protect the fields inside the cladding, and unless those fields are protected, the field which are inside the core also will get disturbed. So, if I disturb these fields will disturb the field at the boundary, this field will disturb these fields, and essentially there will be a leakage of power which will be going from the cladding. That is the reason we have to provide cladding, so that at the outer edge of the cladding, the field would have died down to substantially low value, and these fields are not interfered by the external world. So, as soon as I try to put the fields, the phase fronts inside the rays, I see something interesting happening of the propagation of light. So, let me summarize what we said about total internal reflection. We say that at total internal reflection, there is a standing wave type of fields inside the core, which is this, and we have a decaying kind of fields inside the cladding. In fact, this understanding is required when we go to the more rigorous analysis, which is the wave model. Unless we have this physical understanding, we will not be able to get a solution to the equation which we get from the wave model. And third thing, what is not explicitly seen here, is that is when the ray undergoes a phase change at the reflecting boundary. So, whenever there is a total internal reflection here, suddenly there is a phase change between this ray and this ray at the reflecting point. So, if I consider the 2 points which are very close to each other, this point and this point, the phase between them is not same, and that phase change depends upon the angle of launching, the refractive index of core and cladding, and various other parameters. So, at total internal reflection, essentially 3 things happen. You have a variation of intensity of light in the region where total internal reflection takes place, which is core. decaying fields which extend up to infinite distance in cladding, and there is a sudden phase change which takes place at the core cladding interface. Let us now consider with this understanding two rays which are going like this, and this dotted line here essentially is the phase front which is common to these two rays. Now these two rays, this ray get total internally reflected which comes here, this ray still is going this way, and when it comes here it now get reflected from this point, and this is the phase front corresponding to this ray. So now if I look at this phase front is common to this ray and this ray, whereas this phase front is common to this ray and this ray. Since this is the one ray is the common between these two, essentially separation between these two phase front should be such that you have a phase condition satisfied. That means what is called you have a sustained constructive interference. So the separation between these should be multiples of 2 pi. Then and then only this will sort a set of phase front which are moving this way, and the phase front will satisfy the condition for this ray as well as for this ray and this ray. So if you do a simple algebra for this, what we find is that this distance S1 you can get, which is S1 d upon sin theta, where d is the thickness of this region. S2, which is this, can be written like this. So the difference between S1 and S2 multiplied by the phase constant in the medium of refractive index N1, that is the phase difference between the two rays or two phase fronts, plus we have a phase difference at this total internal reflection and at this reflection, so that is 2 times delta. This total phase should be equal to multiples of 2 pi if you have a constructive interference of light. So what we find now is that we require this condition to be satisfied if the light ray can propagate inside the structure. This is something interesting, because earlier when we talked about numerical aperture, we find that any ray launched at an angle less than theta 0 maximum would have a sustained propagation of light by total internal reflection. Now we say that is not enough. Even within the cone theta 0 max, if the light is launched at an angle which does not satisfy this condition, then this ray cannot propagate inside this optical fiber. And since this m is an integer, we have this expression which gives you discrete angles. That means within the angle theta 0 maximum also, the ray can be launched only at very discrete angles, then and then only there will be sustained propagation of light. So what we have a departure from a solid cone of light to essentially the annular surfaces, over which if the light ray is launched, then and then only it can propagate inside the fiber. If the ray is not launched at that angle, then it will not satisfy the phase condition and it will not be launched inside the optical fiber. So now we have a departure from the continuum theta to a discrete theta domain, and that's what essentially leads you to what are called the modes inside the optical fiber, which are the discrete patterns of intensity of light inside the optical fiber. So following this, in the next lecture, essentially we will develop the understanding of the modal propagation of light, and then we will go to the more rigorous analysis of light propagation inside the optical fiber.